System Exploration, Engineering, and Design, or SEED Lab, involves working within a multidisciplinary team of electrical engineers to design a system to meet the course objective. This semester's final course goal is to design a robot that navigates through an allowable region. At the team's current milestone, our robot has two main functionalities. The first functionality is the robot's ability to determine the angle between the robot's direct line of sight and the Aruco marker. The second functionality of the robot is to take in precise angle and driving distance data and respond accordingly. The robot's design is broken up into four subsystems: computer vision, localization, simulation and control, and system integration.
The computer vision subsection takes multiple pictures and constantly detects a existence of a beacon. And when a beacon is found, it returns the closest beacon in its XYZ coordinate axis, and it also can return an angle. And this was all done by calibrating the camera using a chessboard, and it takes in multiple pictures with the chessboard and multiple angles, and it returns a 3x3 camera matrix, which is the intrinsic properties of the camera, which reduces distortion and allows for the return of the XYZ coordinates. And how this fits into the project is that when it's searching for a beacon, it should be able to detect the distance from the beacon and therefore estimate its distance from the beacon so it's not too far or too close to the beacon.
The localization subsystem of the project involves programming the Arduino to read data from the rotary encoders present on the motors and writing drive values to those motors. The Arduino uses two interrupt service routines along with rotary encoders to constantly track the amount of turns each wheel makes. This data is used to calculate the Cartesian position and angle the robot is in. MATLAB was used to simulate the behavior of the robot based on the localization script. This plot shows simulated behavior of the robot when keeping the right wheel stationary and turning the left wheel in the forward direction.
Immediately following the localization and integration steps, we began this control and simulation step. This was broken down into three different categories. The first one being testing of the robot, the second one being simulation in MATLAB, and then the third step being implementation back into Arduino. During the testing phase, we ran the robot multiple times and gained data about its speed and position in order to create an accurate model in MATLAB. Once an accurate MATLAB model was created, we added a PID controller to it in order to fit the constraints of rise time and settle time. Then we implemented it back into Arduino, and a couple of the problems we ran into is just the practical essence of creating a PID controller. So we had to make a couple of approximations. For one, we had to, instead of integrating, we had to instead make a Raman sum, which was close enough to the integral in order to give us an accurate integral error. And we had another problem where integration would wind up over periods of time. So while it was trying to reach its desired position that entire time, the integral term was winding up. So in order to fix that at certain error values that were large enough, we would just simply delete the integration term until it got into those finer tuned values.
System integration on the robot is done through the I2C protocol. The configuration uses the Raspberry Pi as the master and the Arduino and LCD screens as slave devices. The Raspberry Pi takes in a distance and an angle, combines their data into an 8-bit packet, and transmits that packet to the Arduino. The Arduino then disassembles the data packet and assigns the proper values to command the motors. The Raspberry Pi also sends information to the LCD such as loading notifications and I2C errors.